Alright, so good morning, or afternoon, or evening, whatever time you're watching this. And we're getting to Unit 7, and we're going to go over 7.2 and 7.3 today because I think they all kind of mesh together. We're going to be talking about sine, cosine, and tangent today, and by the end of today, or this session, this video, you should be able to define or understand sine, cosine, and tangent, and how it relates to this angle theta. If you don't understand what this theta is, watch 7.1, and the relationship with triangles, and understand that proportionality. And these are actually functions in mathematics, specifically trigonometry. These are trigonomic functions, and you can use these and have an understanding that right angles, or right triangles with one and other congruent angles are similar because of the angle-angle similarity. This is one reason that this works. Okay, so we have three, let's just get right to it. We have three triangles. We have triangle 1, we have triangle 2, and we have triangle 3 here. So let's identify these different lengths of these different triangles, so we can just kind of start using the vocabulary. And I'll start color coding them too, I suppose, with my straight edge over here. So I'll start, we'll go angle, what did I use? I guess I'll flip it over. I'll use lengths to be different sides here, or different colors. Okay, so we're going to go and we're going to say that, so if you remember, we have the, in reference to theta, remember all these lengths are in reference to the Greek letter theta, but this is the angle theta. Okay, so these lengths that we're defining on these triangles, these are all right angles, by the way, right? So this will be one right angle, this will be another right angle. Change that color to a neutral color between all the different ones. We'll go neutral, gray, neutral triangle. That's a right angle, this is a right angle, and that's a right angle there. Okay, all right angles. So triangle 1. So we'll go. We'll start with the opposite length of each of these triangles. Right. So the opposite length of theta for triangle 1 is this length. I'm going to use burgundy. I think it'll stand out more. Right. Opposite length here is H1 to A1. That's the opposite length. This is the opposite of triangle 1. Let's write that as triangle 1 opposite. We'll do triangle 1 opposite. Yeah, that makes sense. Okay. And that'll be burgundy because our opposites are going to be burgundy. Okay, and then our triangle 2 opposite length, right? This big, long, this bigger triangle, our opposite length of angle theta, right? This bigger triangle, if I cover up the triangle 2 here, would be this length, H2 to A2. Kind of see how I labeled it purposefully. Right, so this would be triangle 2 opposite. OPP is the abbreviation for opposite. And then likewise, my bigger triangle, triangle 3, is going to be labeled. It's going to be, I don't know how well you can see that. Let's scooch it over a little bit so you can see it a little bit better. There we go. Yeah, you can see that better. That's triangle 3. Triangle 3 opposite length. Okay, so that gets all my opposite lengths relative to angle theta. Alright. Remember, theta is just a fancy Greek letter, and it's typically what we use to name the reference angle for all these. All right, so we're going to use the next length we're going to be talking about is the adjacent angle. The adjacent angle is the other leg of the triangle that makes up the 90-degree angle. Okay, if you don't remember that from the last lesson, and we're going to use let's use green. Let's use green for that. All right, so the first theta, or the first adjacent one, would be from here, from B to A1. Our vertex, V is vertex, vertex to A1, vertex to A1, right? And that would be triangle 1 ADJ. Triangle 1 ADJ. And then, so the next one, I'm just going to kind of like scooch it down a little, right? And I'm just going to do this. Whoops. Shut up me a little bit. Do this. That's going to be triangle 2 ADJ. Right? It's this length. It encompasses that length, but it is also this length as well. Right? And then I go down here, and then I have triangle 3. Well, let me maybe add a little more of a gap. A little bit more of a gap there. I have the third one, which is here. This length here. It's triangle 3. It's triangle 3's ADJ. Right, so we got triangle 1 ADJ. This whole length here is triangle 2's, and then triangle 3, they're accumulative, right? So this is equals, you know, if you wanted to do it with line addition postulate, it would be V A1 plus V, well, it's just, I guess you could just say it's V to A2. This is V to A2. V to A2. This is V to A3. V to A1. Right, so that kind of clarifies it a little bit. Okay. Just to remove any ambiguity there. Okay, and then finally, we have the line that's opposite of the right angles for each of these. Right, so this one's opposite here, this one is opposite here, this one is opposite of there. It's the entire hypotenuse of the triangle. Right, so I'm going to use this. I'm going to use orange for this. So the first one is simply this one here. This little triangle. It's that guy like that. So this is triangle 1's hypotenuse, which is, you know, VH1, the length of the vertex to H1. And then triangle 2's hypotenuse is going to be equal to, you know, this whole length here. From here to here. Right, that's going to be V to H2. Right, and then triangle 3's hypotenuse is going to be from here all the way to here. Right, so that's going to be 3. Right, so those are the 3 different line segments that associate these 3 different triangles. All right, so now we just need to kind of measure these 3 line segments and see, and we're going to transcribe the data into these blocks here. All right, so make a little data table. Okay, I'm going to use this handy dandy little thing here. So this is VA1, 2, and 3. These here are the adjacent. These are the adjacent A, D, J. All right, so this looks like this is about, I'm going to say 3.2 centimeters. I'm going to leave out the units. That's about 5.8. It's about 5.8, approximately 5.8. And then this one, I'll zoom in a little. And then this one is about 8.1. 8.1. Okay. And then we're going to do, the next one is the hypotenuse. Our hypotenuse. Okay, so we're going to go, our next one is our hypotenuse. So the first hypotenuse is from here to here. So that is about 3.8. I switch colors to orange. About 3.8. The next one is about 6.5 looks right. Yeah, about 6.5. And the final one is about almost 9. Almost exactly 9. Okay, and now we move on to the opposite lengths. Our opposite lengths. Okay, so our first opposite length is going to be about 1.9, I think. The next opposite length is about 3.1, I reckon. And then the final opposite length is about 4. You can't see it. 4 point. Let's see. That's 1, 2, about 4.3. 4.3. Okay, so now we have all of our data. And now we're going to start looking at some ratios. Okay, and while we're looking at these ratios, I'm going to define these ratios for you, because these ratios in trigonometry have specific functions. I'm going to zoom out so that we can define these for you visually as well. And we did a little bit of this yesterday or the last section too, but I'll have to zoom out a little bit with manually as well with this. Okay. All right, so the first one we have is this opposite over the hypotenuse. Right, so when you have the opposite divided by the hypotenuse, or the ratio of the length of the opposite length of the angle theta over the hypotenuse of the triangle, the length of the hypotenuse of the triangle, that the ratio of the length of the opposite length of the angle theta over the hypotenuse. That is called the sine of theta. That is, I'm going to use purple. That is the sine of theta. So all of these are the sine of theta. And typically, the sine of all of these get rounded to 2 decimal spots, or the thousandths. Round to the thousandths, TH, thousandths, TH, that's thousandths. So 2 decimal points. All right, so you'll see that, you know, there might be some measuring errors in here, right? But they'll be fairly close, okay? So let's plug and chug here, all right? So we'll have our we'll try to minimize transcription errors by being careful with our numbers. So A1, this is 1.9, and then A2, this is 3.1, and A3, this is 4.3. Got my purple for all of my stage my paper here. All right, and now I'll go to my hypotenuse, which is orange. Okay, this is 3.8. This is 6.5. This is 9.0. All right, so let's go ahead and put some numbers in here. 1.9 divided by 3.8. And that equals about 0.5. Okay, 3.1 divided by 6.5. That's pretty close, about 0.48. And 4.3 divided by 9.0. That's about 0.48. Okay, those are all really close, right? About 0.5, approximately 0.5, right? All within plus or minus 2, or approximately 0. If we took the average of those, it'd be all pretty close to approximately 0.5, 0.48 or so. Okay. Remember, there's probably some measuring errors in there. If I measured this one again, I might find it be closer to 0.8. Okay. Now let's see if I do these ones again now. Okay, so if I do 3.8, actually I'm doing VA2. So this one here, whoops, I took up space here. I didn't take up that space. All right, so then next here we have, this is VAs. These are all my green ones, right? These are my adjacents over my hypotenuse. Alright, so I can take these numbers again, 3.8, 6.5, and 9.0, because I'm using the same values. You can see, same values. But now I'm using my adjacent lines, the ones that are, you know, adjacent to the theta, instead of my opposites. This, when I do is adjacent divided by the hypotenuse. This function is called the cosine of theta. I should have changed this to burgundy. Cosine of theta. Okay. So I need to take these 3.2, 3.2, 5.8, and 8.1. Okay. So we have 3.2 divided by 3.8. Those fat fingers, something. 3.2 divided by 3.8. That equals approximately 8.4. 0.84. 0.84. I got 5.8 divided by 6.5. 5.8 divided by 6.5. That's approximately 0.89. 8.1. 8.1 divided by 9.0. That's 0.9. 0.9. I think my 3.8. Measure that again. Measure this hypotenuse again. Looks like it might be closer to 3.7. That might be my issue. What happens if I change this to 3.7? 1.9 divided by 3.7. That made it worse. Okay, let's just keep going with this then. Alright, so then we have, let me double check that math. 3.2 divided by 3.8, 0.84. Okay, so it's just a couple thousandths off. Alright, so then we're going to look at our, now this is our, the next thing we're going to talk about is if we have, so you can see here, by the way, with this cosine, they're all pretty close. They're all within a couple thousandths, right? So, and I'll show you something called the arctan next here, and the arctan, arcsine, and arccosine. So we can actually see what these angles are, what this angle theta is. But anyway, so here if we see this next one is the opposite over the adjacent, and if you have opposite, the ratio of the opposite length over the adjacent length is called, let's see, I'll do pink. It's called the tangent. It's called the tangent of theta. Okay, that's called the tangent of theta. Now let's do purple. Let's do purple, I guess. It's called the tangent of theta. Right. It's also called the tangent of theta. Okay, so if I take the opposite length, but I have these values already, but I can plug them in. All right, so I took my VAs. These are my green values, and I put them on the bottom. My adjacents are 3.2, 5.8, and 8.1. And I took my burgundy values, and I put them on top because those are my opposites. In my numerator, and I put 1.9, 3.1, and 4.3. You'll see that all these are fairly the same too. 1.9 by 3.2 is 0.59. 3.1 divided by 5.8, 5.3 0.53 divided by 8.1 is 0.53. So my first measurement wasn't as accurate as my second two measurements. It varied by just a little bit for all three of them. But let's see how much that made a difference on the angle. Before I do that, let me just kind of illustrate here that as the triangle grew, the ratio of the length to the length to the height to the hypotenuse remained the same. This is just the variation here that you see between these. This is just measurement error, right? But the ratio stays the same, and that's why I'm able to determine a function of the height to the length to the hypotenuse of a triangle based upon the angle theta. Right? And then there's just a really cool thing we'll use a little bit more later on called Arcsine, Arccosine, and Arctangent. Is if we know the value of the ratios like this, we can invert that and we can find what the value of the angle is. Right, that's pretty useful information to know in real life. All right, so say for instance I knew that this length and that length were this long, and it yielded the ratio value was, or the sine was 0.48 or 0.48, right? And I knew that was the sine, right? I can just push this inverse sine button, and I know that this angle here is about 28.6 degrees, right? Same thing with this one. If I do 0.89 inverse cosine, it's about 27 degrees, right? So I'm pretty close, and the measurements that I take, if I do 0.9 inverse sine, 0.9 inverse cosine, it's about 25.8 degrees. They're all really close, within a couple of degrees. So if I was like, my max variation here, from here to here, 0.84 to 0.89, 0.84, that's 32 degrees, to 0.9, 25 degrees. So that's a 6-degree variation, just because of 0.06 thousandths, or just because of 6 thousandths off. So that is a pretty significant change when you're talking about carpentry or anything like that. 6 degrees variation is a pretty big deal. So when we're measuring these, make sure we're measuring them as close as we can, but we are limited to the tools that we have. Right? The tools that we have really our limitation. Okay. So let's move on to some examples here. All right, so we're given that let's figure out, we're given that for these two angles. We'll say that angle F, and we'll say that is theta for angle F. Orange theta is angle F, purple theta is angle F, and orange theta is angle A. Okay, so we'll do, what do we say? Our hypotenuse is always, let's just not take that approach. Okay, so for theta, in this case, we were using purple as the neutral color here. Okay, so theta in this case, okay, in both of these cases, our hypotenuse is orange. Right, our hypotenuse is 20. Right, so for both angles, our hypotenuse is 20. So for all of these, 20 will be our denominator. Okay, Hypotenuse isn't used in tangent, so we're not going to use the hypotenuse in tangent. So this is our hypotenuse in both cases. Okay, so for angle F, our opposite is that one. Oh wait, opposite, what do we use opposite? It's burgundy. Opposite is this one, and our hypotenuse is this one. Or sorry, our adjacent is this one. Okay, so for angle F, our opposite is 16, and our adjacent is, oops, I did that wrong. I did the colors wrong, but that's okay, is 12. Opposite is 16, and our adjacent, opposite is 12, and adjacent is 16. Okay? And then for our, well, we should still do tangent too. Alright, so tangent, our opposite is 12, and our adjacent is 16. Okay, if we shift the theta to angle A, the opposites and the adjacents change. Our opposite is now 16. Our adjacent is now 12. And it's just now going to be 12 over 16 for here. Okay, now that we have all of the values plugged in, we can determine what all this stuff is. We can figure out the sines and the cosines, and we could even figure out the angles if we wanted to, which we will. Although I think that that is beyond the scope of this lesson, but I'm still going to do it because it's just an extra button push away. Alright, so 12 divided by 20 equals 0.6. 0.6. So if I wanted to figure out what the angle was, let's do inverse sine. That's 36 degrees. 36.9 degrees. Okay. The cosine is 16 divided by 20. That's 0.8. That angle would be 30. Oh, wait a minute. 12 divided by 20. 0.6. Inverse sine. 36.8. 36.9. And 16 divided by 20. Inverse cosine. 36.9 degrees. Okay. Alright, and then 12 divided by, oh, that makes sense. Yeah, that makes sense. Okay, and then so 12 divided by 16 is 0.75. Inverse tangent is 36, 0.75. That's 36.9 degrees. So that makes sense. Those all should match the same. This all should be the same. Okay, and then for over here, the angle A, well, if this is 90 degrees, this is this was approximately 37 degrees. You should suspect 37 plus 90 equals minus 180. You should suspect this to be about 53 degrees, right? So let's see if we did our math right. 16 divided by 20 equals 0.8. The inverse sine of that is about 53 degrees. We did that right. 0.8. And that was about 53.1. 12 divided by 20 equals 0.6. 53.1. 16 divided by 12. Tangent. Oh, 1.3. Inverse tangent. 53.1. Pretty cool. Okay. I'll do another one. Now we're going to determine a length based upon what we know here. Okay, so we know that we have theta, and we have these two here. So the first thing we need to do is we need to figure out the length of TL, right? So we use Pythagorean's theorem for this. This is a little review from yesterday. So this is we don't have a coordinate plane, so you could use Z if you wanted, or A if you wanted, or C if you wanted to. I'm still going to use Z. My X is my Z squared equals X squared plus Y squared. My Z squared is going to be equal to square root of 35 squared plus my Y squared is the square root of 42 squared. Each one of those equals 35 plus 42, because I squared both one of those. It's 35 plus 42. So 35 plus 42 equals 77. Alright, so Z equals the square root of 77. I don't think that that's a perfect square. No, it's not. It has 7 and 11 in it. That's about it. This is the square root of 77. Okay. Alright, so now I gotta figure out this. My sine is my opposite over hypotenuse. Alright, so this is gonna be opposite is square root of 35 over square root of 77 equals, alright, so I'm going to do 35 square root divided by 77 square root equals, it's 0.67. And then cosine is adjacent, 47 square root divided by 77 square root equals, so it's cosine is 42 square root 42 divided by adjacent 77, and that equals 0.78. And tangent is opposite over adjacent, so square root of 35 over square root of 42, that's going to be equal to 35 square root divided by 42 square root equals 0.92, 0.91, and I'll use that to figure out this angle. This angle here is 42 degrees. So if that's 42 degrees, 42 degrees plus 90 minus 180 means this is 48 degrees. So, cool. Alright, so now, trigonometry is so awesome. So easy. Okay, so this one here, I got these two here that are super easy. Okay, I know that this is 72 degrees. And I know this is 30 degrees. Okay, this is the power of trigonometry right here. Okay, so let's put this together. If I know this is 32 degrees, okay, and I want to solve for, let's say yes, I want to solve for x. This is the hypotenuse. Well, you can't see it. Okay, let's do this one. If I want to solve for x right here, and this is the hypotenuse, if I know that the sine of theta equals the opposite over the hypotenuse. In this case, it equals the x over 84.2. Right? Let me do some simple algebra here. Let me get rid of this. So I just did some simple transitive stuff right there. Make that equals x over 84.2. Okay. Right, so now I'm going to multiply 84.2 times the sine of theta equals x. Now, do I know the sine of, do I know 72? Do I know theta? I do. So I do 84.2 times the sine of 72 equals x. So if I know this angle, and I know one of these lengths, I can figure out this length. Okay, so I do 72. I press the sine. Oh man, that's pretty awesome. I multiply that by 84.2. And bingo bango, x equals 80.0, 80.1, round to the nearest tenth, because that's what it's given in. X equals 80.1. Man, that's awesome. Right? Now I could use Pythagorean's theorem to figure out why, but why do it? I know the cosine of theta. I know that the cosine of theta equals y over 84.2, because it's adjacent over hypotenuse. Right? So I can do this, except that's going to be cosine. Right? So it's going to be 84.2 times the cosine of 72 equals y. Cosine 72 times the cosine times 84.2 equals y equals 26.1. 26.1. Right, now to prove that to you that works, right, I'll go 26.1 squared, 26.1 squared plus 80.1 squared equals 84.2. Right, now there's rounding errors in there and stuff like that too, but it's really, really close, right? In fact, this is more accurate than the rounding is, right? Because this is all trigonometry. Trigonometry is awesome. Real life applications, carpentry, electrical, like all sorts of cool stuff, right? So this is, I love trigonometry. It's so easy. Okay. Alright, so now we're going to find z, and we're not given the hypotenuse this time, we're given the opposite. Alright, so the math's a little different. Okay, we're still going to set it up that we'll do the sine. We could even use tangent. We could figure out the tangent, but I like using the sine. Sine of theta equals opposite, or x, in this case, right, over z. Well, that doesn't work because I don't have x or z, so let's use cosine. Equals y or z. I have y, right? So this is going to be equals 68. 68. Okay, so I'll do some algebra. I have z times the cosine of theta equals 68. Right, now I need to have z equals 68 divided by the cosine theta. Z equals 68 divided by the cosine of 30 degrees. So this is the way I do this. This is the way I put it into the calculator. Okay, I do 30 degrees cosine, and then I invert it, and then I multiply that by 68, and I get that z equals 78.5 5, 2. That's one way to do it. Okay. Another way to do it is just do 68 divided by 30 cosine. You get it the same way. Okay. Just work it out first, right? And solve for what you're trying to solve. Okay. Now to solve for x, it's gonna let's do working with tangent. Tangent equals opposite over adjacent. Okay. Equals x over y. I don't have x, but I have y. So tangent equals tangent theta equals over 68. Right, so x equals 68 times the tangent of theta equals, I have 30 degrees. Take the tangent of that, multiply by 68, equals 39.26. 39.26. 39.26. Okay, so that's how you do all that. You could have figured out that is 60, and you could have used another trigonomic function to figure that out over there if you wanted to. Right? Multiple ways to figure this if you understand sine, cosine, and tangent. They are very powerful functions for right triangles. Okay, I hope that helps out you guys. Pretty long lesson this time, but it covered 2 sections. And you can find a copy of this on the Focus lesson. And man, this really made me excited because I love trigonometry. Wait till we get to the unit circle. If you have any questions, please feel free to ask.